Okay, so it's 10 o'clock. I think we can start. First of all, I'd like to welcome you all for this webinar. Today it will be Ulrike Weiss, our product application chemist for spray drying, and myself, Aurélie Demont, who's product specialist for spray drying, who will give you the information. So the first question that some of you might ask or have already heard as a question is, what is spray drying? So we know that spray drying is a widely accepted method to evaporate aqueous and organic solvents, and the sample can come as a solution, an emulsion, a dispersion, a suspension, and then with spray drying we will make it as a dry powder. Spray drying is really good for volume reduction, to maintain the chemical or biological stability of a product. With spray drying we can also obtain a defined particle size, and it's a really interesting process if you want to do, for example, matrix microencapsulation, so to do co-processing and also to do agglomeration. So quickly, how does spray drying work? I will explain it a little bit, since we saw that many people don't have that much experience into spray drying. So here we see a drawing of a spray dryer, and how spray drying works is that you have your sample that you will feed through a nozzle, and this nozzle will spray your sample in a drying chamber. Then in order to dry it, we will bring an airflow of hot air that will enable to dry those small droplets of sample, and then the small droplet of sample will dry little by going down the drying chamber, and the dry powder will be collected in the product vessel after passing through the cyclone. So basically the centrifugal force inside of the cyclone will get the powder to drop in the product vessel, and the drying gas to continue through the filter via the aspirator and then to be expelled in the atmosphere. When you dry a droplet, some people might say, oh, but since there is heat, it's going to be a problem for my sample. It's not, and I will explain it to you now. So basically what happened is that we have a co-current air stream. So the feed and the hot gas are entering inside of the spray dryer at the same side of the drying chamber. So the hot gas will be in contact with the feed at the highest point of humidity of the feed, and then the evaporative cooling will prevent the temperature to increase inside of your droplets. So the heat will be transferred to the droplets and be used to evaporate the liquid and will not heat up your product. And then there will be a decreased temperature gradient with the ongoing drying until the product is dry and will land in the product vessel, and then it will be exposed to the outlet temperature of your spray dryer. So your product will never be exposed at a higher temperature than the outlet temperature of your spray dryer. So spray drying could then be the answer for quite a lot of processes. Can be the answer to improve bioavailability of a product, for example, or to improve the dissolution rate as well. It's good to improve release property of a product, and since we can optimize the particle, it is good to for aerodynamic particle size. And then you need to optimize the process condition for that, or you can optimize some stuff through the process condition. For example, the residual moisture can be optimized, the particle size, the density of the powder, the flowability, and the compressibility as well. So there is important attributes and benefits of the powder that can be applied to spray drying. So with spray drying, you can define the particle size, the flowability, the compressibility. You can also work on the bulk density. You can do some granulation and agglomeration, some taste masking of a product, work on control release property, increase the bioavailability, the residence time of a product in the body, and you can do encapsulation in one step. In order to do all that, you need to work with some excipients sometimes, or some binders, or some encapsulants. And here we have a list of all of these. I'm not going to go through all that, but we can see that they can come either from polysaccharide and derivative. Some of the most known are probably maltodextrin or mannitol or trehalose or lactose, but they can also be synthetic. And in the synthetic, most of you probably already heard about colidone, for example, from BASF. There is PLGA, which is quite well used as well, PVA, HPMC. So a lot of those synthetic excipients are also well used in spray drying. So we can see that on this slide, we show all the type of applications that are possible with spray drying. So we could do like simple drying. Like for example, a good example would be coffee or milk powder. So you have a liquid product, you chuck it into your spray dryer, you have a droplet of your product, and then you end up with solid particles. So that's just simple drying like everybody knows. But you could also use your spray dryer to do amorphous solid dispersion. We will come back to that in a further slide. To do some structural change, for example, micronization or agglomeration and granulation. This will come also later. Or you can do some encapsulation of liquid and solid. So if we start with encapsulation, the advantage of spray drying for encapsulation is that you can have one formulation or a single feed to do some encapsulation. So you can do encapsulation of oil. Commonly we do that with maltodextrin and or gum-arabic, but you can also do encapsulation of solid particles. And the advantage of encapsulation is that you can work on controlled release, you can improve the stability of your product, you can do taste masking, you can protect your product from the environment, you can do some coating to up to some extent. So that's more or less the advantage of encapsulation. Spray dry amorphous solid dispersion, this is something that's really well used into the pharmaceutical industry to improve bioavailability of some product. So when you want to work on amorphous solid dispersion, you need to figure out what's the solubility of your API, in which solvent your API is soluble, and then you need to find a polymer that's also soluble in the same solvent. So you need to pick a solvent to use for both. It's really important as well to figure out the glass transition temperature of your product and of your polymer. And you will need to determine the best ratio of API and polymer to work with. Then once you have all those information and determine all those parameters, so the concentration, the ratio, the glass transition temperature, and the solvent, you need to figure out if other additives are needed to protect your API, for example. And then you create a solution of all of them, and you can spray dry it. So amorphous solid dispersion is really to improve bioavailability of a product by putting it into an amorphous phase. Then there is spray drying of protein, which are really important for biotech and biotherapeutics. Here we have to understand that we work with a temperature sensitive product. So it's important again to know the sensitivity of the product so that we can aim our outlet temperature to be lower than this temperature sensitivity. What's also important is that the molecular weight of the protein can be too high, and then we need to lower the concentration. If you work with protein or biomolecules, you also will need typically to work with some cryoprotectants because you need to protect your molecule from the heat and from the drying process as well. So commonly used cryoprotectant can be trehalose, mannitol, lactose, and some buffer solution. And you will need to work on the ratio of your bioactive and the protectants. Also, sometimes you will need to use some surfactants. And then again, once you've figured that all out, you will be able to spray dry your product, and you will need to set your parameter so that the outlet temperature of your spray dryer gets lower than the sensitivity of the product. Agglomeration of nanoparticles are really commonly used at the moment in the ceramic industry. It's something that's really trendy now. So this is quite a simple application. You have your nanoparticle, you use a binder or an excipient to make them stick together, and then you can spray dry them and agglomerate them. As I said, this is really used in the ceramic and inorganic nanomaterial material science. So here they use a lot of agglomeration and granulation to improve their process. The commonly used binder are mostly PVA and PEG. Some of the applications, for example, are about agglomerating graphene for batteries. You will need to determine the percentage of binder compared to your solid. You will have to usually you will want to have the highest loading possible, but you'll have to be careful because of the amount of binder you need. It might be too viscous to go through your spray dryer. You may need to have some additional surfactant for the flowability and the droplet formation, and also to avoid the nozzle clogging. Then we see as well that we could work or dry product in two different ways. We could dry it with spray drying, or we can dry it with lyophilization or freeze drying. Here we see a difference in the morphology of the product, and we see that with spray drying we really have a more flowable powder because it's a spherical particle that you can produce. So the shape and the size will play a big role in the processing afterwards. Thank you very much. So now we will talk about how to optimize your process parameters and how to optimize your process. So I will let Ulrike talk.
Right. So hello. As you can see here, this is the process, the parameters we have on our spray dryer. So we have what we can change is the inlet temperature, the aspirator, the pump speed, and what we haven't shown here, the gas flow of the spray gas. What we what can we only passively influence is the outlet temperature. So first I would like to talk about the sample feed rate. In general, here you can see always the feed rate, and then you can also see the parameter that is mostly influenced by it. So if we increase the feed rate, the outlet temperature will decrease because we have at any point more solvent in our system. That takes more energy to dry, and that directly influences the outlet temperature, which then is lower. It will also have the particle size will get bigger because there's bigger droplets, which will then give bigger particles, but it will also increase the humidity because the spray dryer might not be able to dry this much at any given point. Then let's talk about the outlet temperature. This is something, as we talked about before, this is a temperature which you want to be keeping an eye on. So if your product is temperature sensitive, you need to have a look that this temperature stays below that the outlet temperature keeps below the sensitivity of your product. So as I said before, on a lead spray dryer, you cannot set your temperature and outlet temperature, but you have to play around a bit with the inlet temperature, which has and the biggest impact is the sample feed and the spray gas. It is a generally misconception that the T outlet has to be 100 degrees if you're using water. That would be the T inlet temperature, and the T outlet temperature would roughly be 40 to 50 degrees below, depending on what you're drying. So if you have something that is temperature sensitive at 80 degrees, you can dry it at an inlet of 120 and it will not break. And this is what generally makes a spray dryer so attractive, because you can go in with a high temperature and it will not destroy your product. Now, let's talk about the gas flow rate. the higher you have the flow rate of your spray gas, the smaller the droplets will be and the smaller the particles will be. It also will result in a lower outlet temperature. In generally, what we often see is that people, customers who want to have big particles are trying to decrease the spray gas flow. However, if the spray gas is too much decreased, what we often see is a spraying against the wall, against the first third of the spray gas cylinder, and that is because then our conus of the spray is too flat and we spray against the wall and we will not be able to dry anymore. So in generally, I would always say if you want bigger particles, play around with the feed, with the concentration of your sample and not with the gas flow rate. In generally, we say anything between 30 and 40 is a good spray gas flow for most applications. There's always the odd one out, especially if you work with solvents where you can go lower or higher. But in generally, this is where I would give a starting parameter for. Another one I just want to say is, because we had this question as well, a bit of spraying against the glass cylinder, the wall, is normal. That is because we have quite a violent gas flow, air flow in the system. So some of it will flow back and this will land on the wall. So if it's just a bit, that is very normal. If you really see a ring of product on your cylinder, this is not normal, and this is probably then an issue you have either with the nozzle cleaning or that the gas flow is wrong. So in generally, this is also, you should have with your B290. Here is a general process parameter overview and what influences what. So we can see, because we have a lot of questions as well, we will answer later about the particle size. So you can see the biggest influence on the particle size really is the spray gas. But again, I wouldn't, because at one point you come to the point where your process is not working anymore if you play wrong with the spray gas flow, but then really the feed rate and the solid concentration. The higher your concentration, the more product is in any one droplet, the bigger your particle size is going to be. And if you are struggling with spray drying, and because they're temperature sensitive, but you would like to have a bigger feed concentration, but then you can't dry it anymore, I would always say try to swap it for an organic solvent instead. So this is also a tip, is if you struggle to get what you need with drying water, have a think if you can swap your water out for an organic solvent, because often you can go lower temperatures, which will be better for your outlet temperature. You can have a higher spray gas flow because this organic solvent dries faster, and you can have more feed rate because you don't need as much energy to dry the same amount of solvent as you do with water. So, because we had so much questions about particle size, I just wanted to have a little talk about the particle size. So in general, we can say we in Büchi, we offer two different nozzles. We have the two-fluid nozzle, which is assisted with air, and we have an ultrasonic nozzle. Using an ultrasonic nozzle gives us bigger particles, but what it actually does is it shifts the mean particle peak further to bigger particles. But you can see on the graph that even there, the highest possible particle size we can feasibly get is 40 to 50 microns, with a mean around 25 for the ultrasonic nozzle and around 10 for the two-fluid nozzle. This is due to the drying path that we have in a lab unit. So the drying path is all of the parts of the spray drying cylinder, and that is around a meter for a lab unit. If the droplet is too big, and we are talking about droplets that give you a particle size of around 50, 60, they are just too big and there's no way we can dry them in 1 meter length. So we are physically constricted by the size and the path of drying we have. If we are talking about bigger particles, we need a further drying length, we need a wider drying chamber as well. And then we are talking about a pilot scale unit. So really, if you want anything about 60, you would have to swap to a pilot scale unit. However, it is very, very hard to understand and optimize your process on a pilot scale. And really, this is where we come in with the lab scale. And everything that works on a lab scale is quite easily scalable to pilot scale. So, as we had talked before, we have seen there's a lot of people who struggle with sticky products. This can have two main problems can be there. There's either the problem that the product is still wet. So it will stick to your cyclone if the humidity is too high. So there are a few ways we can change this. So one way is we can increase the aspirator, but if it's already at 100%, this is not something we can do. We can, of course, increase the inlet temperature. If this is not possible because it is temperature sensitive, as I said before, always think about, can I swap my water for an organic solvent? Of course, then you would need a B295 and work under inert conditions. Maybe you can increase the solid concentration and with this decrease the water you have in any droplet. Or you need to maybe go down with the pump. A second thing that could be the problem is the glass transition temperature. The glass transition temperature is where our product, our polymer, turns into a rubber, turns a morph. So when I say polymer, people often think only about synthetic polymer like PGL, but sugars are also polymeric structures. So we're really talking here about any polymeric structure. And as you can see on table 1, if you look at something like glucose or fructose, this has a glass transition temperature of 5 degrees and 31 degrees. That means at 31 degree outlet temperature, your glucose will turn into a sticky rubber and will stick to your cyclone. When you see like a rubbery kind of blob on your cyclone, then that means that you need to have a look at your outlet. Either you need to decrease your outlet temperature, but as you can see, glucose, fructose, 31 degree, 5 degree, we cannot dry water and still have an outlet temperature that low. So what you can do is you add a second excipient that raises your glass transition temperature. So a glass transition temperature is often a mix of the glass transition temperature of all of the ingredients. So if you have seen before, if you spray something like orange juice where you have a lot of glucose and fructose in it, it will not work alone. So what you can do is you can add either lactose or maltodextrin, which have quite a high glass transition temperature. And then you have a flowable powder because you raise the whole glass transition temperature of your mixture. So we are through with our webinar, and now we have a few questions, and we have a few questions which we got in advance as well. So maybe we can answer a few questions now. So the first we have is about the airflow in the spray dryer. We have talked about this a bit in the beginning. So essentially the airflow in the spray dryer is mainly influenced by the aspirator, which is essentially like a hoover pulling the drying air into the heater and then through the system. But you will always have a bit of a currents in the spray cylinder because at this point you also meet the spray gas which gets pumped in. So there's a lot of currents in there. It is very hard to track them properly in a lab unit, but once you go into industrial one, there's all kinds of programs to track them, to see them, to make them visually. Then we have aseptic spray drying for pharmaceuticals and vaccines. Aurélie, do you want to?
Yeah, I can take this one. So with the Bushy spray dryer, it's not possible to work in aseptic condition. It will be possible in a pilot industrial spray dryer, but not with a lab scale spray dryer because there is no possibility to do cleaning in place or to sterilize the instrument. Then we have a next question about measurement of liquid density. Would it improve the spray drying process and avoid nozzle clogging? Is there other tests that we can do before?
In principle, yes. So in principle, we have a maximum viscosity of 300 CPS that we can, or whatever you can still pump through the pump. However, it really has to be looked at from case to case, because often where we see nozzle blocking is when we work with slurries. So when we work with ceramic slurries, for example, and ceramics tend to like to dry, and we are also working at a lot of high temperatures. So what happens there is that they dry, that you can have a look, I can have a point where they dry immediately at the top of the nozzle, at the exit of the nozzle, and then it will block. And there you wouldn't, density measurements wouldn't help you in this case, because it's not a solution, it's a slurry. So then as next we have how do you reduce the cooling on walls? How do you prevent the atomizer from blocking up? At what temperature should you preheat? I think we answered this, that you have to look at nozzle maintenance, cleaning, the spray gas you have to have a look at, and of course sometimes it's just also a case that your concentration is too high and you need to reduce the concentration to avoid. For example, I once sprayed sodium chloride, and at 20% sodium chloride, I completely blocked my nozzle. 10% is fine. So sometimes it really is just having a look at your formulation. Is there too much binder in there? Is the concentration too high?
Good. Then the next question is about how can we obtain core shell particle with a spray dryer. So basically, and this is linked, maybe we will link it to another question that we have in the chat about encapsulation. So basically, when you do an encapsulation, you will create an emulsion of your polymer and the product you want to encapsulate. So for example, if we do an encapsulation of oil, we will create an emulsion of the oil with the maltodextrin solution, and then we will spray dry this emulsion. So what we will get is that we will get some inclusion of oil inside of our maltodextrin matrix, and that's what we will get. So you won't be able to have core shell particle where you have a very one big defined core and one defined shell around it. You will really have some small inclusion of your oil inside of your maltodextrin matrix. Then the next question is about how to handle volatile and hazardous ingredients.
So the question is a bit multifaceted. If you are asking about volatile solvents, we offer an inert loop for this, because volatile solvents need to be spray dried under inert conditions so they don't self-ignite in the spray dryer. And for that we have an inert loop which will condense the solvent out, and then you can spray under inert conditions under nitrogen or argon gas. If you are talking about volatile products like self-igniting products, we cannot handle them in the spray dryer, and we can also not handle any solvents that would form peroxides. If we are talking about toxic materials, we cannot work aseptically, so we cannot include the spray dryer into a fume hood.
Then the next question is about maintenance. So about how often do we need to clean our aspirator, our inner loop, So I think for how often, it really depends on as well how often you use your spray dryer. But if you use it quite intensively, I would recommend you to clean your aspirator on a 3-month basis. If you see that you have a lot of particle going into your filter as well, then maybe you should clean it on a monthly basis. It really depends on how often you use your spray dryer. What also happens is that if you really see that your aspirator is dirty quite quickly, maybe you should change the airflow pattern in your spray dryer, and instead of having it into suction mode, you should maybe switch it into pressure mode. If you have trouble with it, it's explained in the operation manual, but if you have trouble with this, our service technician can always be contacted to help you.
Then we also have a question about what is the importance of the dehumidifier. The dehumidifier is essentially an air con for the unit. So if you work in either regions where the temperature, where the room humidity is very different from one season to the next, or you work in an area where you always have a lot of humidity, part of your energy of spray drying, if you work in open mode, would go into drying this surrounding air. So if your dehumidifier would pre-dry your air, and keep every experiment the same conditions. So you always go in with the same kind of air. And if you work with a solvent and water mixture, you will need the dehumidifier, because otherwise your B295, your inert loop, would freeze, and that would destroy the inert loop. So you need to get rid of the water first, and there you would need a dehumidifier.
Good. So then we also have a lot of question about scaling up of particle size. Basically, on a lab spray dryer, the highest particle size that you can aim at is around 30 to 40 micrometer. You won't be able to go higher up, not because the spray dryer cannot produce the droplets that are big enough, but because we do not have a long enough drying length. So if you want to produce larger particles, then you will need to go into a pilot scale or an industrial scale spray dryer. And there you will have a long enough drying distance to produce particle which will be above 100 micrometer easily. But you cannot do it on a laboratory scale spray dryer. Then we have another question about encapsulation, which is, can we encapsulate using this 3-fluid nozzle?
We can still not do what you, if you imagine actual core shell particles like an egg, we will not be able to do this even with the 3-fluid nozzle. What we can, what I always would say, where you use the 3-fluid nozzle is really if you do not want to use surfactants to stabilize your emulsion, and you have two different parts of the emulsions that are really very unstable. Then you can feed them together in the 3-fluid nozzle. They meet at the tip, and there you encapsulate. But it is not really possible for us at the spray dryer to do a core shell particle like an egg. For that, depending on the size you want, I would look into the encapsulator. Then we have as well that what you, if you want to use a gas spray flow of 50 to 60, if you use a gas spray flow of 50 to 60, you have very small droplets, and a very violent almost flow of air. So this, you might be able to dry it depending on your inlet temperature. With the water, I would be careful, because you might just spray it onto the bottom of the spray cylinder. but I know that if you use an organic solvent, especially one that likes to dry very fast, like DCM, 50 to 60 is an option if you want very small particles.
Then we also see that there is question about the nano spray dryer. I cannot tell you if there will be a webinar about nano spray dryer at the moment. Then there is a question about if it's possible to scale up the nano spray dryer process, and there it's a bit of a two-side answers. If you have a nano spray dryer because you have very low amount of product and you have very expensive product, but that you are not interested into the small particle size, this is a process that you can scale up. So basically, if you want to see if you can spray dry a product with the nano spray dryer because you have a low amount of product, and that then you will go with bigger particle and higher amount of product when you see it works, yes, you can scale it up. And you can go to the mini spray dryer afterwards and then to pilot and industrial scale, no problem. But if you have a nano spray dryer and you want to scale it up while keeping the very small particle size, there the scale up is difficult because what you will need is to have multiple nano spray dryer in parallel. So you cannot do it like with the mini spray dryer and go to a bigger instrument. This is not possible. What you will need is to have multiple heads in parallel to be able to scale up your process.
So we have the question as well of how inlet temperature and the flow rate influence the particle density. The particle density is normally influenced with how fast your particle dries and how well, while drying, your product dissociates back into the solvent. So if you have a big dose, if it likes to dissociate back into the solvent like a salt and water, you'll have a very dense particle. If it dries very fast and doesn't like to go back into the solvent like a slurry, you will have a hollow particle. So you can play around a bit with the aspirator of when you have lower aspirator rates and high inlet temperatures, you will dry slower, lower inlet temperatures in a low aspirator, you will dry slower and have more hollow particles. However, because as we said before, the short drying path on a lab spray dryer, it's very difficult to really play around with the density there. Once you go bigger, lab, in pilot or industrial, you have a lot more room to really turn and fine-tune your particle density because you have a longer way, so you have more chances to dry slower, faster. And for whoever asked these questions, look up the Peclet number. This is the basis theory for density and for how the density behaves in a spray dryer.
Then we have another question about how much spray drying is useful in plant extract. I think this really depends on what you want to do. We see a lot of application, for example, of spray drying in traditional Chinese medicine where they have a lot of plant extract that they dry and formulate via spray drying. We see it as well in cosmetic at the moment that they extract a lot of ingredients from the plant and then they formulate them on a solid excipient using spray drying. So it's quite useful, but it really depends on the application that you want to have. I'm still looking down the list of questions. I think we've answered most of them.
We also have a question, one more question about spray congealing. So essentially, what we now talked about was spray drying, which is when you go in with a solution and you evaporate a solvent. What is also possible is to go in with a melt, with a hot wax, and then cool it. This is essentially done, and there you also would need the humidifier depending on the melting point of your wax. So there we go in with gravity. We do not go in with a spray gas, and we let the melt fall through the nozzle, and we cool it with the surrounding air. And then you can get a powder of a wax. If there is more questions in general, so we hope we have answered all of the questions to your satisfaction. If not, you can always contact us. And we also have an email. This is application@büchi.com. And there, if you have an application-related question, you can send us an email, and we will can then also elaborate more than we have time here.
Good. Then I see as well that there is some question about the presentation. The webinar has been recorded, and you will be able to find it on the Büchi YouTube channel, same channel where we have the maintenance video and all those videos that are useful. So you'd be able to find a recording of the webinar on YouTube. If there is some question that we haven't answered, or that we haven't answered up to the level you wanted, please do not hesitate to contact us, and we will try to answer you as best as we can. Then I think we've been through it. Thank you very much for attending and for answering our little survey as well. This will really help us to aim later on for really the problem you have in our webinar, instead of doing something a bit more broad like we have done today. So thank you very, very much.
Thank you as well for me. And have a nice day.